Today we're going to work inside of section 9.2, which is called Multistage Experiments. Yes?
Is 9.2 due Friday?
Yes, it will be. Yeah, we'll start 9.2 today. We'll finish it on Wednesday. It'll be on Friday. Yes. So 9.2 is an extension, like a continuation of 9.1. In 9.1, we talked about what probability kind of means. We talked about, we didn't define them this way, but we called them single stage experiments. We rolled the dice one time. We picked a card one time. So we just did one experiment and we did it one time. We talked in general about Bernoulli's law of large numbers as well, which is a repeated process kind of thing. But we still didn't look at what happens when we do something a specific number of times beyond one. So that's what we're going to look at today. So in particular, we are going to be working with tree diagrams. Tree diagrams are a sample space model where each outcome is designated by a separate branch. Now, the stuff we did back in section 9.1 were called one-stage experiments. They're experiments that are over after one stage. We roll the die one time and it's over, okay? And if you were looking at rolling the die one time and it's over, and you looked at a tree diagram, I'd like to show you what one would look like for, actually let me do something simpler because there's 6 outcomes when I roll a die. I just want to do a briefer kind of a picture. Let's say we're flipping a coin, okay? So what you're going to do is you're going to put a dot, and there are only 2 outcomes because when you flip a coin, you either get heads or tails. And so you draw 2 branches out from there. So you would do a branch for every outcome. If we were doing my rolling the die, we'd have 6 branches. And we label what those outcomes are. So for this one, it's heads and tails. If we were doing my rolling the die, we'd have the numbers 1 through 6. If you were choosing cards, you might somehow kind of decide between, like, maybe it's red and it's black, or maybe it's the different suits, or maybe it's the different numbers. It's kind of depending on what the question's asking you. But for these, there's just 2 outcomes. And then along every branch, we're going to put the percentage, well, the probability that that branch happens. So for this one, it's a 1/2 probability you get a heads and a 1/2 probability you get a tails. The same thing would be happening for the die problem, except they'd all say 1/6, because there's a 1/6 chance you roll each individual number. Now, not all experiments are equally likely. We encountered that sort of idea last time when we did our cards example, and there was a question that asked us if these following events were equally likely, and it was like red and black, and we said yes, and then it was like face card, not a face card, and we counted things up and we said no. So the numbers along a tree diagram don't always end up being the same probability, so you have to be a little bit careful on that. Just because there's 2 branches doesn't mean they're equally likely. So pay attention to what the question's actually asking in the context. Now, a 2-stage experiment is an experiment that's over after 2 steps. So in the case that I've got on my board right here, this would be like flipping a coin twice. Okay? So if we were flipping a coin twice, I'm just going to show you what it looks like in comparison. So a 2-stage experiment, we would start out looking just like this one already did. We'd start out with a dot, and we would write our heads and our tails, and we would write our 1/2 and 1/2. But then what would happen is off of the end of each of the H and the T that are listed there, we'd have another set of branches. So if I rolled a heads and then I rolled again, if I rolled a tails and then I rolled again, this would be the tree diagram sort of collection of options, what can happen. So if I rolled a head, or sorry, flipped a head, I could either flip another head or another tail. The same thing's true if I did it again, right? Heads and tails down here. And again, each of those are equally likely. I have a 1 out of 2 probability, or 1 out of 2 chance of those things happening. So again, my tree diagram represents outcomes that are equally likely here, and that's not always the case. Okay, and then if you wanted to know, we'll get to this in a moment, but if you wanted to know what happens along a specific branch, and I'll refer back to this when I do, like let's say you want to know the probability of getting heads and heads, both. You could figure out that by multiplying along that set of branches. You do 1/2 times 1/2, and you'd get 1/4. So tree diagrams are a visual that helps us to imagine what's happening. So I'd like for you to sort of put a bullet point in your notes. Actually, it's written down out here. This is what I was just talking about. Multiplication rule for tree diagrams. For all multi-stage experiments, the probability of an outcome along any path is equal to the product of the probabilities. So if I want to know the probability of getting the heads and heads, I go along the head-head path, multiply the probabilities 1/2 and 1/2, get 1/4, and that's what it is. So this is the note that I was verbalizing just a second ago. I just hadn't flipped my screen. You should have tree diagrams or something equivalent, and I'll show you what I mean by something equivalent when the opportunity presents itself, okay, on all your problems. Now, I am fully aware that if I asked you on this particular problem, what's the probability of getting heads and heads, right, 2 heads when you flip the coin twice, you could probably do that without any tree diagrams. But the more complicated the problems get, the harder they are to picture that happening. The reality is, on this particular one, if you wanted to know what's the probability of getting heads and tails, right, I just flipped it twice, and I flipped it twice, and I got 1 head and 1 tail. Well, there's actually 2 outcomes that have it happen. There's this outcome here, heads, tails, and there's this outcome here, tails, heads. And what I can do, just like I mentioned before, is I can multiply along the branches, right? This is 1/2 times 1/2, which is 1/4. And 1/2 times 1/2, which is 1/4. And then I would add up the individual branches results together. So this would be 2/4, ends up being another 1/2. So the more complicated the question, the harder it is to do it without a tree diagram. That said, sometimes it's a lot easier to ask you an easy question and you just to show me the work in the tree diagram, so that's why I've required it that way. Okay, so there will be a tree diagram or something equivalent on every problem that you're asked to do, whether it says to do one or not. Okay? Some of you are still going to turn in work without tree diagrams. Don't let it be you. Highlight this or something, okay? Okay, so let's talk about a couple other things, and then we're going to do some examples. Independent events. I alluded to this last time. We actually talked about it a little bit. Independent events are events in which the occurrence of one event has no influence on the outcome of a second event. So, for instance, you could say that the weather today might very well affect the weather tomorrow. Those would not be independent events. But the weather today and the weather 3 months from now, those would be independent. Very little to do with one another. They're so far spread out. My example where I was flipping the coin with the heads and the tails, those are independent events. Every time I flip, the probability resets. We actually talked about that last time as well. The probability resets, and I have a 50-50 chance, right? It doesn't matter what I got last time I flipped the coin. This time, I have the same 50-50 chance again. And when I have independent events, the probability of them both happening is simply the product of them happening. And that's what you saw happen over here, right? When I multiply along a branch of a tree, I'm finding those probabilities. When I put the probabilities into the tree, I decided whether or not they were independent and made my assertions at that point. But that's what you're seeing happen on this particular example, is this multiplication along the branches of a tree. So that happens anytime there are independent events. All right, example number 1 has a scenario that's a lot more complicated than my coin flipping. Okay, we're just jumping right in with a hard example. This one, it talks about a committee. It consists of 10 members. There are 4 women and 6 men, and 3 of them are selected at random to attend a meeting in Hawaii. Now, in theory, you could draw a tree diagram with 10 branches because there's 10 people. There's 10 different possible outcomes. But that's not really all that necessary based on the questions that are actually being asked. So if you flip your page over, or you can look at the screen, you can see the kinds of questions they're asking, which help you to decide how to draw your tree diagram. The questions that we're asking are having to do with the probability of selecting women versus men to be in this committee. So when I'm looking back over here, I don't really need to know the individual probabilities of each individual person. This question's asking it based on their gender, right? So when I'm drawing my tree diagram, that's the only identifying feature that I need to be concerned about. There's some other examples in your homework and so forth that do the same thing. You draw you've got some buckets of letters, and you're drawing out letters and you're wanting to spell a specific word. Well, if I'm wanting to spell a specific word, either I get the first letter I need or I don't. I don't really need to know what happens every time else I get every other letter in the bucket. I only care, did I get the letter that I needed to spell the word or did I not? So be careful as you're looking at the questions. That helps you to determine how to draw the tree diagram, okay? Usually it simplifies things if you're being attentive to the questions being asked. So on this one, we're going to select 3 members to go to Hawaii, right? It says that we want 3. So we're going to draw the tree diagram first, and then once the tree diagram has been drawn, we will be able to answer the questions pretty directly. Now, we're going to start with a dot, right, just like I mentioned before, and there are only 2 outcomes based on the type of information that I'm being asked to answer questions about. You can write it as man, woman, male, female. I don't care what you want to do. It looks like I've got mine written as a man, woman, men and women. So, can you imagine we have a bucket of names, and we've got the names of all of the, the people that we're concerned with, and we reach into the bucket and we pick one out, okay? What is the probability that I select a man's name? Okay, let's keep it in the unreduced form. 6/10. I know it reduces, and you're welcome to do that. I just want to show you something else kind of cool that happens in this process. And if I keep it in its expanded looking form, it'll be easier to see that connection. 6/10. And what's the probability I select a woman's name? 4/10. You bet. Okay, everybody good so far? Okay, once I've done that, I don't put the person's name back in. They're going to Hawaii. They don't get to take the trip twice, right? Like, that doesn't make sense. So sometimes things replace. We put the items back in, and sometimes they don't. Oftentimes it will say that you replace it or you don't replace it, but sometimes too, it's like common sense. I wouldn't put the person's name back in because they've already been selected to go. Does that make sense? So as I draw my next set of branches, I'm going to draw the branches understanding there are no longer 10 names in the bucket. How many names are in my bucket? 9. So what you actually see happen on this one is that every denominator is now out of 9. Because there are only 9 names remaining. These sort of look like I'm writing repeating bars on something I'm not. I promise we'll put a fraction numerator on there in just a second. But again, we have men and women. Now, the fractional portion of these probabilities that I'm writing down, they depend on where I've come from. So for instance, if I've already drawn out one man's name, I'm on the top, how many men's names remain in the bucket? There's 5. But if I'm down below and I'm looking down here and I've drawn out a woman's name, how many men's names are left in the bucket? There are still 6, okay? So it matters where you are as to what those numerators are going to be. Along the top as well, you can do a couple of things. I'll do it directly with you and then I'll show you the connection. Again, if I've drawn out a man's name, how many women's names are still left in the bucket? 4. And you'll notice, and I'll make, I think there's a note on it actually later, but you'll notice that if you do the 5 ninths and the 4 ninths and you add them together, what do you get? You get 9 ninths. Every time you look at an individual component of the tree diagram, the probability has to add to 1. Has to. Now, using that fact, can you tell me what the number here has to be? It has to be a 3 because 3 plus 6 is 9. And sure enough, if you consider from the characteristic or the perspective of looking at the actual scenario for a problem, 4 women's names, I pulled 1 out. There's 3 left. Right? Okay, so we've got 2 people that have already been now selected from this process to go on the trip. But we're supposed to have 3. All right, cool. So we're going to draw one more set of tree diagram branches off of the end of these. And we've got a bunch of M's and W's again. If you're having difficulty sort of extending your branches to have enough space, that happens frequently as you first start this. The longer you make your branches out, the more space you'll figure out. The more bunched up you try to space that out, like all on the left-hand side of your paper, it becomes this sort of looks like a fan instead of like a tree. It doesn't really matter what it looks like to me, but it becomes harder to manage your space. So if you just elongate your lines that are coming out as tree branches, it usually gives you more space to work with. Okay, so we're going to do one set of branches at a time. Along the very top, I've selected 2 men so far, right? So how many men are left? 4 men left out of how many names total? 8. How many women are left? Still the same 4 because none of them have been selected along that branch. Okay, the next pair, I've selected 1 man and 1 woman, right? So along this branch right here, made it too far, but along this branch I've selected 1 man and 1 woman, okay? So how many men's names are left in the bucket? 5. Should be 5 out of the 9. There were 6 originally and I selected 1. How many women are left in my bucket? I don't mean out of 9, I mean out of 8, I'm sorry. 3, because there were originally 4 and I selected 1. So this is 3 out of 8. This branch right here is quite similar in the fact that I've selected 1 woman and 1 man already. So the probabilities actually match the ones I just did. 1 man's name has been drawn, so there's 5 out of 8 men left. 1 woman's name has been drawn, so there's 3 out of 8 women left. And then along the bottom branch, I've already selected 2 women to go. So how many women are left to choose from? We'll do women first. Yeah, 2. So 2 out of 8. And we have the same 6 out of 8 men that we started with. Any questions about the diagram first? Because if you don't get the diagram, you can't answer the questions. Okay, so let's look at the questions that are being posed to us. A, what is the probability that all 3 selected are women? So I'm going to highlight that in yellow. And then I'll do my next stuff in the different color. This is the only branch where I have 3 women selected, right? And what would I do to find out the probability along that branch? Multiply them all together. So I had 4 out of 10 times 3 out of 9 times 2 out of 4. 2 out of 8. It's going to reduce. Okay, fractions. That was chapter 6 stuff, right? You got lots of choices. You can multiply across the top, multiply across the bottom, and then reduce. Or you can reduce where they start with already. So I usually like to reduce first because the numbers become smaller quicker. For instance, the 4 and the 10 both have a 2 in common, so I can divide them both by 2 to get 2/5. The 3 and the 9 both have a 3 in common, so I can divide them both by 3 to get 1/3. And the 2 and the 8 both have a 2 in common, so I can divide by 2 to get 1/4. Even if that's the only reducing I do on this problem, that's quite a bit. So I'm going to just pause right there and multiply what I have, and then we'll reduce further at the very end. So I have 2 times 1 times 1, so that's 2. And on bottom, I have 5 times 3 times 4. What's that? 60. Of course, 2 over 60 is still not quite all the way reduced. I can divide them both by 2. And what will I end up with? 1/30. Typically speaking, we're going to work with whatever type of number we start working with. For example, on this one, in theory, could you change it into a decimal? Well, if it were a nice decimal, you could, but this one's not. It's not a nice terminating decimal, so it wouldn't be a good idea to do so. We'd lose some accuracy, okay? But there are going to be some problems where the proportion or the probabilities that you're given are in decimal form, so you just leave them in decimal form and you work with decimals instead. Okay, so we're going to use decimals on some, we're going to use fractions on some, and sometimes you just have a choice, right? If I had done my example over here with the heads and tails, I did fractions. We could have done decimals just as easily, right? Because the fraction 1/2 is a very nice decimal 0.5. So sometimes you have some choices. Okay, there's one more question that's that is asked here, part B. It says, what is the probability that at least one man is selected? So take a look back at your diagram. If you have some sort of a color that you can mark them in some way, mark all the branches that you see that have at least one man selected. So we should have highlighted the top branch and the second, the third and the fourth, the fifth and the sixth, and the seventh. We highlighted everything that we didn't highlight before, right? We did. Everything else has at least one man that's going on the trip. So, you have two possible ways to proceed. One option is to multiply all the probabilities along each of those individual branches. Right, so we can multiply 6/10 times 5/9 times 4/8, and then 6/10 times 5/9 times 4/8, and then 6/10 times 4/9 times 5/8, and then 6/10 times 4/9 times 3/8. And we can do that along every single branch, all 7 of them. And then we can add all that together. That's one possible way of doing the problem. And you will get the right answer. It's a lot of work. The easier way to do the problem is to recognize that this is 1 minus the probability of having all women. In other words, it's 1 minus the probability that we just got, hang on, let me do it like this, over here. We already found the probability of having all women. It was 1 out of 30. So if I take 1 minus 1 out of 30, what's that going to give me? 29 out of 30. And that's a lot faster than doing 7 separate multiplications and then adding, right? Oh yeah, lots faster. So pay attention to places where it seems like that's going to be really cumbersome. There's going to be a lot of multiplication in that step and then an addition, and see if there's another option that allows you to do it in a more seamless fashion, quicker, right? This would be an example of one. So this is a fairly complicated tree diagram. It's complicated because there's 3 sets of branches. It's complicated because the probabilities change at each juncture. You have to pay attention to what was previously done to know what's happening now. That makes it a kind of complicated problem. The one we did originally with the heads and tails is a pretty straightforward one. Either there were smaller numbers of branches, which there were in both cases, my single experiment and my multi-stage one. But it was also simpler because the probabilities were the same on every branch. So I'd like to do an example now for you of one that is, like it says here, or something equivalent, right? The work that would look something equivalent, so you can see what that might look like if you weren't doing a tree diagram. And example number 2 is a good example of that. A box contains 5 slips of paper, numbered 4, 6, 7, 8, and 9. A player reaches into the box and draws out 2 slips and adds them up. If the sum is even, the player wins. If the sum is odd, the player loses. Okay, so can you picture what's happening in this scenario? Okay. Now we could do a tree diagram. We could do this. We'd have 4, 5, 6, 7, 8, and 9. And then we'd have branches 4, 5, 6, 7, 8, 9 off of each of the 4, 5, 6, 7, 8, and 9. And it'd be a big tree diagram. It'd be really messy. But if you take a look at what the outcomes are going to ask us in terms of the question, the probability the player wins, and then part B is a little bit different. But them winning or losing doesn't really have to do with the individual numbers that are selected. It has to do with whether they add up to something even or something odd. Does that make sense? So my outcomes really aren't my individual number picks. My outcomes are whether or not the picks end up giving me an even or an odd sum. So what we're going to do is we're going to actually write out all the different outcomes that we can have when we grab two numbers. And if we can do it in an organized way so that we don't miss anything, it'll be a lot easier for us to make sure everything's there. For example, I'm going to start with just the number 4. I could draw a 4 and a 5. I'm sorry, there's not a 5. 4 and a 6. I could draw a 4 and a 7. I could draw a 4 and an 8, or I can draw a 4 and a 9. And those are all the different ways I can draw 4 with something. I'm going to go back and add them together in a moment. I just want to write down all the different draw possibilities first, okay? So I could probably also just not draw 4. So instead of drawing a 4 with anything, I can now collect all the different ones with 6. Well, I already wrote down 4 with 6, so I'm not going to start back there. So I can draw 6 and 7, or I can draw 6 and 8, or I can draw 6 and 9. And those are all of the outcomes that have a 6 in them. I can draw a 7. Again, I don't need to write down 4 and 7 or 6 and 7. I've already written them down. So I can draw a 7 and an 8 or a 7 and a 9. And then the only possibility I haven't listed now is what? Yep, 8 and 9. So we're going to go back and we're going to find the sum of each of these. Again, the point is we want to see whether they're even or odd. All right, so let's go back and catch these real quick. 4 and 6 is 10, 4 and 7 is, 4 and 8 is, and 4 and 9 is. Awesome. 6 and 7, 6 and 8, 6 and 9, 7 and 8, 7 and 9, good, and then 8 and 9. 17, right, good. Okay, so going back and taking a look, we will win if we have a even number, right? So we need to count how many evens we have. There's 1, 2, 3, 4. I got 4. Did you get 4? Okay. There's 4 evens out of how many? There are 10 possibilities, yes. So I've got 4 out of 10. I can reduce that then to what? 2 over 5. Or if you really wanted to change this into decimal form, it works very nicely actually, and you could do that too, right? Because this is a terminating decimal. So either the 2/5 or 0.4 would be fine. So that's the probability that the player wins. Part B changes the rules a little bit. It says, well, what if this happened instead? On Part B it says, will it change the probability if we multiply the numbers instead of adding the numbers? So let's go back and think about what happens if we multiply. In particular, we know that we're looking for evens. So I'm just going to change my color. I'm not going to write all these down as to what their product actually is. I'm just going to highlight them if they're even. Is 4 times 6 even? Yes. 4 times 7? 4 times 8? And 4 times 9. Okay, so I hope those of you who was saying yes so much for me over here. All right. So, Marissa, how did you know that those were where the answer was yes so quickly? You were multiplying it in your head. Did anybody do it differently? Emma, what'd you do?
Well, it's almost like, when they multiply by 2, the answer would be evens, and multiply by 4, the answer would be.
Yeah. So one of the ways you can do it is to multiply in your head, like Marissa said. Another way that you can do it is like Emma said, where you could look at it and you could just say, hey, look, if I have an even number in it, it's going to have to multiply to give me even. And if I do that, I automatically get all the 6s. And I get the 8s. Practically get everything, don't I? Almost every one of them had some kind of a portion of it that was an even number that I was multiplying. So how many of them did I highlight in yellow this time? 9 of them out of the original 10. So does the probability change? Yes, it does. And it changes to 9 out of 10. Any questions on that? Okay, I think that's a good place to stop, so we'll pick up with example 3. Example 3 is another one where we can do some written down work that's not quite a tree diagram as another option, so you can see what that would look like. So we'll pick up there next time.